All right. I saw a bunch of folks with their homeworks out, so it's probably not a bad idea that we do this. And if you've got questions, please feel free. Remember, your homework is due on Friday, and so today is our last lecture together before the homework is due. So y'all know what I like to do. I like to open it up to any questions that you may have. And see, I know some of you are like, here's the thing. We don't have like a solutions manual that we can download off a torrent site or something because Dr. Mike makes all the homeworks custom. Shucks. Well, they must be able to read my mind because I came up with these problems myself. I am. Are there any questions, though, about homework 2? I mean, the floor is open. So. Really? I would have started it already.
Plus or minus an hour?
No.
2 hours?
Oh, it's going to take you a little bit. Yes. Hold on. I got to be able to hear. Yes. Mm-hmm. Are you talking about solving for a maximum length? I mean, what you can say is this. Let's make up some numbers. If you calculated a maximum length of, 25.9 feet, I mean, I'm okay with you just saying 25.9 feet is the answer, but I wouldn't say, well, let's round that up to 26, because that's going to violate, so it would be lower. So now, be clear, when you compute that, if you're using a radius of gyration in inches, the answer, like just numerically, is going to be in inches, so you'll need to convert to feet to make that a little more usable. Well, the question is just asking, if I remember correctly, just what's the maximum length before you violate it. So I just want to know that. You wouldn't use that. It's just, if I'm evaluating the section, here's the maximum length. So the idea is, if it was 25.9 and it was being used in a building where it was going to be 30 foot long, yeah, that's a problem. So. Any other questions? Okay. It's due on Friday. All right. So today, what we're going to do is we're going to do a design problem. Start to finish. We are going to, it's lecture 10, and we're finally going to do some steel design. Let me say a couple things, though, about the design process and the procedure. First off, and let's be absolutely clear, in design, you are making assumptions. So let's be clear. I can get you a trial section for this example 5 in like 30 seconds. The key word is trial section, okay? We are making assumptions in order to arrive at that cross section. We must validate those assumptions by analyzing the shape, okay? So what I don't want to see on a design problem is you plug and chug into this expression and you find a W10 by 49, you're like, I'm done. No, you're not done. You have no idea whether or not that section is valid, so you need to analyze that section, okay? That's point 1. Point 2, again, to be absolutely crystal clear, okay? If you compute an efficiency 90% or better, you're good. It is possible that during the process of design, it is possible that, let's say you compute an efficiency and it's 90.01%. It's possible that if you were to actually analyze the next slide of shape in the manual, that it might actually work. I'm not going to make you do that. I'm of the opinion that if you can analyze one section, you can analyze 80 sections. So I just want to see you go through the process. In a real-life design scenario, you'd have Excel, you'd have every resource to your heart's content. In a 55-minute exam, you just don't have that. So don't worry. It's okay. Third, and this is going to become very clear on this example, and it's going to be clear on the homeworks and the exams. Let's take a look at this example. Okay, so I want to design this tension member. The tension member is subjected to 130 kips of dead load, 110 kips of live load. And just so everybody's aware, unless otherwise noted, the loads have already gone through live load reduction. So we won't need to go and reduce the loads. We might do that at the very end when we talk about beams, but we're not going to worry about that right now. Here's the thing, okay, where it says right there, it says, let's select a W12, okay? So what that means is, for this problem, we're going to design a W12 by something to resist these loads, okay? The reason I'm doing that is because I am placing some restrictions on the problem so that we all arrive at the same answer in class. If I just said design a tension member, how many members are in there? How many shapes? A lot, right? There's probably 30 or 40 different shapes that are economical and all work. I don't want to grade 30 or 40 different problems where everybody has different answers and they're all right, okay? So I'm going to be placing some restrictions so that we all arrive at the same answer. But the process is going to be exactly the same, okay? So when I say design a W12, it means it's going to be a W12 by something. Again, the most economical section, okay? Now, member's 30 foot long, got the dead loads, live loads on it. Okay, I'm assuming A992 steel. I'm going to point something out about that here in a little bit. But we're going to select the lightest W section. Remember, in design, we're going with the lightest shape in here, okay? I also decided to mix it up a bit on the bolts. We're going to use 7/8 inch diameter bolts on this problem. So the bolts are going to be a little bit bigger than what we've been using throughout the class. Sound good? All right, so before we begin, before we do any math, I'm curious, what's the first step? What's that? Come on, don't be shy. What's the first step? What's that? Well, we can't, I mean, we could do that. Oh, you're talking about AG men? How do we do that? What do we need? Well, we open up the manual and look up the shape for what? We're in design mode. We have no idea what the shape looks like. Guys, I think you're thinking too much about it. What's the first thing we need to do? Say it again. Say it louder. There we go. We got to factor them loads. You folks in concrete who's had concrete design, y'all should have known that. All right. My goodness. All right. So, first thing we need to do, factored loads. So we have a dead load of 130 kips and a live load of 110 kips. So we need to factor that load. And so what does that come out to be? 332 kips. Do I have a second on that? That's a great question. Now, remember, live load reduction is intended to account for the probability that not the entire tributary area is being loaded. But when it's all said and done, there's still uncertainty associated with that magnitude. Hence why we apply that load factor. So keep in mind, so for instance, we're applying a 1.2 load factor for the dead and a 1.6 load factor for the live. Okay? We're still applying a higher load factor because even though we perform reduction, there's still more uncertainty associated with the live load than there is the dead load. All right? Think about it like this. If I have a W10 by 49 that's 50 foot long, how do I determine its dead weight? Just take the 49 and multiply it by 50. I can be pretty certain of that. However, I'm going to be a lot less certain about how much load is on this floor. So that's why we're still applying that load factor. The reduction is just a code provision to take that maximum load that's specified in the code and reduce it to something that's a little more usable, but there's still uncertainty associated with it. This is a good question. This is a good question. Anybody else? Now, we're in design mode. We have no idea what this section looks like. But what do we know about this cross-section? It's a W12, but what else do we know about it? The type of steel. And what type of steel is it? It's A992 steel. So what do we know about A992 steel? The FY and the FU. And so what are those values? Oh, goodness. I'm making y'all do work. Now, I want to point something out on this table. Okay? Give me a sec. Does anybody notice these little gray and black and white squares next to the stresses? Did y'all notice these right here? What do those mean? Okay, if there's a black square, what does that mean? Preferred material specification, and then gray is other applicable material specification, and then white means it doesn't apply. Here's sort of a rule of thumb of what that means. If I go down to Huntington Steel and I purchase a W10 by 49, chances are it's going to be made out of A992 steel. Okay? If I go purchase, let's say, an angle, what do you think it's going to be made out of? A36. Okay? The point I'm making is this. If you don't know, go with the preferred material spec. So in this problem, I told you to assume A992 steel, but what if I didn't tell you that? What would be the value that makes sense? The preferred material spec for that shape. Because that's generally what you're going to find. That's generally what the mills are rolling. Okay? Make sense? So if I don't give you that value, go with the preferred one. Okay. Now, everybody good? Okay. Now, bless you. Now remember, what we're doing is we've got a factored load and we're in design mode. So when we're in design mode, what that means is we're trying to select a cross-section, okay? And in order to select a cross-section, we need some limits, okay? So I got two limits here that I'm going to employ, a limit on the radius of gyration and a limit on the cross-sectional area. So let's take the cross-sectional area first, okay? So, excuse me. Design expressions. Now what I'm going to do is off here to the side, I'm going to compute a couple values. The first one is 0.9 Fy. So that's 0.9. Sorry, I wrote that incorrectly. I wanted that in parentheses. So that's 0.9 Fy. So that's 0.9 times 50 KSI. And that equals what? 45. And then 0.75 squared times FU. Now remember, the reason that we square that is because one of those is our phi value of 0.75, and the other is our assumption for the effective net area. Okay? And so we made that other 0.75 is there to make an assumption. That's there to make our math easier. So this is 0.75 squared times 65. Have a second on that? Okay. Now, why did I do that computation? because our gross area limit says that we take our factored load and we divide it by the minimum of those two. Okay? Why the minimum? Because that's going to be the worst case scenario. Okay? So I propose that we then say AG min is 332 kips divided by 36.6 KSI, and that equals what? .08 what? Square inches. This is an area. And do I have a second on that value? Good. All right. Now, that is our first design limit, is the limit on gross area. We also have a limit on the radius of gyration. Okay? Now, the radius of gyration limit is L over 300. Okay? And so L is what? How long is this member? It's 30 feet, right? Divided by 300. But that's not going to be very usable because all of the radii and gyration, or the radii of gyration in the manual are expressed in inches. So what I'm going to do is I'm going to throw myself in a little unit conversion. 12 inches per foot. So again, write out those units. Yes?
For AG min, shouldn't it be divided by 0.9 times FY, which would be the 45%?
Well, we have two limit states. We have our gross section yielding and our net section fracture. So here's one way of thinking about this problem. Based on our assumption about net area, I'm saying net section fraction governs, that this is going to be the worst case scenario. Again, though, it's based on an assumption, so I might be wrong. We'll see here in a second. So, okay, going back to R min, what's our R min limit going to be? 1.2 inches. Do I have a second on that? Okay. Everybody good so far? All right. So here's what we're going to do. All right. We have a trial shape that I want to look up. An AG min of 9.08 square inches and an R min of 1.2 inches. Now, before we look anything up, this is a W shape. So when we look at the R's, should we be looking at RX or RY? RY. Remember, for W shapes, the minimum is always RY. So here's what I want you to do. We're looking up a W12. Let's open the manual, and let's find the lightest W12 that meets both these limits. You got it?
No.
Yeah. Anybody got a shape for me? A W12 by 35. Okay? Now, first off, let's list some properties. So first off, what is the AG for a W12 by 35? 10.3. And what is the RY? 1.54. What is the next lightest W12? A 12 by 30. Why didn't you pick that one? The AG is 8.79. Okay? So there's a reason that you didn't pick that next lightest one. Sound good? Does everybody else see that? Okay. Now, at this point, this becomes exactly like the last problem that we did. This is a trial section. We don't know if this section is going to work because we guessed some things. We guessed some things about the effective net area. We got to do some math and check this thing out. Okay? So I'm going to ask for a few properties. I can do better than that. What's going on with the flange thickness? 0.3? You got outvoted. You're right, that's the web thickness. All right, flange width? I like hearing that everybody's using these decimal values and not these fractional values. All right, and the depth. Remember, if you have a W12, the depth is about 12 inches, in this case 12.5. All right. Sound good? All right. So at this point, again, it's a trial shape. So we need to do some analysis. Let's do some analysis. Okay, so I'm going to scroll down a bit. So first off, the net area. What's going on with the net? Yes?
Is this just the section you want us to use, or how would we know exactly how many bolts we're putting over the spacing, like 4 inches?
What do you mean?
The spacing of 4 inches for the bolts, is that something we design, or that comes standard?
We'll design that later. For now, I'll give it to you. But we'll design connection. We'll do connection design later. We do the tension member stuff first, and then we start laying out bolted connections, and then we lay out welded connections. So don't worry, we'll get there. Everybody good? All right, net area. How many bolt holes am I going to subtract for the net area on this section? 4, right? Is everybody okay with that? Samurai sword or lightsaber? 1, 2. All right. Minus 4 times the hole diameter times the flange thickness. Okay? So that is, so tell me what to write. What's the gross area? 10.3. Remember, we're using the actual gross area of this section because we're analyzing it. So 10.3 inches minus 4, and the hole diameter, what do we do? You add an 1/8 to the bolt diameter. So what I'll do is I'll write 7/8 plus 1/8. And then the flange thickness is 0.520 inches. Okay, and so what does that net area come out to be? 8.22. Do I have a second on that? .22. What shear lag cases are going to apply for this section? So obviously case 2. And I heard case 7. That's exactly right. All right, so we need some connection eccentricities and we need some connection lengths. Okay, let's start off with the connection length. How long is this connection? It's 8 inches, right? Outer bolt to outer bolt, 8 inches. So what about the X bar? What do we do there? We need the Y bar for a what? A WT 6 by 17.5. What is the Y bar for a WT 6 by 17.5? 1.3. Is everybody able to find that? Remember, this is the special case for W shapes. Okay? When you have W shapes connected via the flanges, you turn it into an equivalent WT. This is the only time that you do that. Okay?
What was the reasoning behind that again? Was it just like a trick?
It's part of the empirical expression, but the idea is, give me a sec. The idea is that if you have a section that's connected like this, the behavior is like half the load goes up here and half the load goes down there. That's kind of the idea. But again, keep in mind, this is empirical. It fits the test data. You can't really derive it. It's just sort of is what it is. Go back to our problem. There we go. All right. So therefore, U2 equals what? Say it again. 0.84. I think if you carry it out, it's like 0.838, something like that. Everybody okay with that? What about case 7? Does case 7 actually apply? And why is that? It says 3 or more fasteners per line. Do we have 3 or more fasteners per line? How many do we have per line? 3. We have 3 fasteners per line. So we have case 7 that we need to assess. And how do we assess case 7? What do we need? We need BF, and we need 2/3 of the depth. Okay, so BF, what was that again? I got it here. I'm making sure y'all paying attention. 6.56 inches. Okay, and this is 2/3. I think that was 12.4. There we go. I knew. I was just making sure you're paying attention. What is this? 8.33. All right. So, excuse me. So, BF and 2/3 the depth, that's bigger. And so, what's U for case 7 going to be? And so, what U value do we use? 0.85. Are we okay on that? All right. In order to determine which limit state governs, I'm going to compute both of them. Okay? So, what we're going to have is 0.9 FY AG. Then we're going to have 0.75 FU ANU. So this is 0.9 times 50 KSI times what? 10.3. All right. And this one is 0.75, 65 KSI. And this is, what was the net area? It was 8 point something? 8.22. And then U was 0.85. So let's do the top one first. What's the top one? 463.5. Do I have a second on that? And what about the next one? 340.6. Do I have a second on that? All right. So which one governs? 340.6. Now lastly, and I like to do this at the end just to ensure that there's a summary, just to make sure I didn't do anything completely incorrect, I like to compute my L over R ratio. So this is 30 feet times 12 inches per foot divided by, what's R again? 1.54. And so what does that come out to be? $233.7. What's that? What? You're getting ruled over. I'm hearing 233. Or now. 233.8. Are we in agreement? Okay. All right. So let's summarize what's going on with this problem. And I like to do this at the end to make sure that we have a holistic view of what's going on with our design. Okay? So let's do a summary. All right, so what was PU? 332. Okay. What was PPN? What is our design capacity? It's the 340.6. That's the one that governs. So first off, is this section valid according to strength? All right. L over R was 233.8. Okay. What I like to do at the very end is compute my efficiency. I can do better than that. And so what does that come out to be? Let's express it in a percentage. We'll say like to one decimal place, like a percentage. 97.5%. Is that an efficient design? Yeah, it's pretty good, yes. Yes. That is a great point. That will become relevant later, but remember, right now we're yanking. That's if we're squishing, okay? Let me give you a more elaborate explanation. When we start talking about compression, we're going to start talking about buckling, okay? There are shapes in the manual that have slender elements, and by slender elements I mean like the flange and the web, and they have a susceptibility to experience what's called local buckling. The idea that the flange and the web might crinkle before the whole thing buckles, okay? We'll talk about local buckling later, but for now, recognize that that's a compression issue. We don't need to worry about that because we're not pushing on it, we're yanking on it, so it's tension. You might see similar notes with a little F on it or a little V on it. You can ignore those as well because the F will correspond to flexure for bending and the V is for shear. And you don't have to worry about those either. Sound good? So what's the answer to the problem? I'm curious. Well, what's the answer? There you go. The answer is use a W12 by 35. The only thing that might be a little mysterious is where did the dead load and the live load come from? There's a simple answer. It comes from structural analysis. Y'all remember how to analyze a truss? Analyze a truss, you got some dead load and some live load in that truss member, 1.2 dead plus 1.6 live, bam. I'm not making you analyze a truss because I have done that before. I have made you do that before. I know I have. Are there any questions about this problem? This is important. Like, this is steel design. What if it didn't work? What if it was over 100%? What if this didn't work? What would you do? Go to the next one. So we're on a W12 by 35, so what is the next one? Is it a W12 by 40? So analyze the W12 by 40. Will that possibly happen to you? Yeah. That's life. I can't really avoid that. What if the efficiency came out to like 70%? Go to the next lightest one. I mean, that's just, it is what it is. Will you have to iterate? Yeah, it's possible. I will do my absolute very best to reduce that iteration on exams, because if you can do it once, I think you can do it twice. I don't really see the point in making you do it twice. But is it possible that you have to iterate on homework assignments or in real life? Yeah, it is. Bless you. That just is what it is. I can't really. Yes. I have no problem with that. Y'all are grown-ups, but y'all are going to use Excel on the exam. So, but I have no problem if you want to iterate on Excel and hit print. I really don't. But I got to be able to interpret that homework assignment. What do you think? This isn't bad, is it? Take a piece of steel, yank on it, determine the area. All right, I need y'all to pay attention. Let's talk about some soil mechanics. I'm serious. I'm going to bring up something in soils. All right, everybody calm down. Have you seen that before? Oh, God. All right. Chill out. Everybody, shh, relax. Everybody, shh. Pay attention. Okay. Now, bear with me. You'll see where I'm coming with this. All right. If you remember, there are 3 limit states that we're assessing in regards to tension member. There's yielding, there's fracture, and then there's that weird one, that block shear one, right? Okay. Now, before we start talking about block shear, I want to take some time and talk about something related to the behavior of steel. And I'm going to try and relate that to something that I'm pretty sure you have at least seen at some point in one of your classes, namely soils, okay? So let me recap and re-review that in case it's been a while since you've seen that in soils. Okay, now, if you have a piece of steel and you yank on it, when does it yield? Well, it yields when the stress hits Fy. That's easy, right? One stress, one load, one stress. Once the stress hits Fy, it's yielded. But what if you have multiple stresses going on at a given point? When does that element experience failure? Okay? For instance, if you have an element of a stress element, if you're looking at a foundation or you're looking at stress in a soil, when does it fail? Well, it's not as simple as when the stress hits some value, because you've got normal stresses and you've got shear stresses going on at the same time. If it's a clay, it has a cohesion value, angles of internal friction, all this stuff. There's a lot of different parameters. So how do you determine whether or not that element experiences failure? Well, it depends on what we call a failure criterion. I promise you have seen at some point a failure criterion related to soils. This expression here is one of the most famous soil mechanics expressions that, for determining failure in soils. It's called the Moore-Coulomb failure criterion. This equation is pertinent for materials that are brittle. Okay? So soils, in research you'll see this used for concrete. This is for brittle materials. Okay? Would that make sense to use this equation for steel? No. Steel is not a brittle material. Steel is a ductile material. Okay? Now, like I said, a simple yielding criterion or failure criterion, for instance, if you're just yanking on it, is when the stress hits Fy, it's failed. That's easy. Okay? Has that yielded? I have no idea. Okay? Because there's a lot of different stresses going on. Remember, in 3 dimensions, you have 6 different stresses that can go on. You got 3 normal stresses and 3 shear stresses. So how do you determine if that stress state means failure for a given material? Well, it depends. It depends on the stresses, and it depends on the failure criterion that you're using. So Moore-Coulomb failure criterion would not be appropriate for steel because that is a criterion appropriate for more brittle materials. For ductile materials, the failure criterion that we use is what's called the von Mises criterion. Okay? Now, here's the equation. You don't have to memorize it. Don't worry. Don't worry. But the idea is that given a state of stress, you start plugging your stresses into this expression, and if this expression is held true, then the member experiences failure. Okay? Why am I telling you this right now? Because it's important when you have stresses that are in shear. Okay? Let's say you had a state of stress that was nothing but shear. Okay? So every one of these normal stresses are 0. We have one state of pure shear. So we have one shear stress and everything else is 0. So you start canceling everything out, and you start plugging and chugging, and you find a very interesting find. See, if you're taking a member and you're yanking on it, it yields when it hits Fy. But if you're taking a member and shearing it, it doesn't fail at Fy. It fails at a stress far below Fy, specifically around 0.577 Fy. Okay? Now, what happens in the steel manual is the steel manual says, let's just call it 0.6. Okay? So if you open the manual and any limit state related to failure in shear, it's funny how there's a 0.6 that shows up every time. Okay? The reason why is because under shear, steel fails at around 60% of the yield stress, or particularly 57.7% of the yield stress. I'm showing you this because I want you to recognize when you see this value show up where it's coming from. Okay? So why is that relevant here? Well, block shear rupture, if you remember that failure where the chunk sort of rips out of the member, that is a limit state that is a combination of shear and tension. What happens is you're yanking on the connection. So here's my plate, and I'm yanking on it like this. What happens is these paths on the left and right, they are experiencing shear. So it's sort of a combination of failure in tension and failure in steel. Okay? This is an image of a test that was done at Georgia Tech. This is an image of a test that was done at WVU. I showed you that video on YouTube. So, I mean, this actually happens. It's a very real possibility. So, like I said, it's a combination of a failure in tension and a failure in shear. How do you compute the capacity? Here's how you compute the capacity. Now, I know you're seeing this equation, you're going, oh my goodness, this is ridiculous. Like, FYAG was bad enough. What the hell is this? You got RN equals a pile of crap less than or equal to another pile of crap? Like, what math are you talking about, Dr. Mike? You lost your mind. Well, first off, let's take the variables and break them down a bit because it's really not that complicated. There's a lot of like AGVs and ANTs. The computation's pretty simple and the naming's pretty simple. So for instance, what is AGV? It is the gross area in shear. What is AGT? It is the gross area in tension. What is ANV? It's the net area in shear. You kind of see where this is going? Now, one of the things you're not going to find in this equation is AGT, the gross area in tension. But you can't calculate the net area in tension without calculating the gross area in tension, so we're going to have to compute it anyways. Okay? So that's point one. We've got our nominal capacity. The phi value is 0.75. But one of the things I still haven't answered is what the hell's going on with the equation? Like, why is it a pile of junk less than or equal to a pile of junk? Like, that doesn't make sense, okay? Well, whenever you see an expression like that in the specification, that is the specification's way of basically saying it's the minimum of those two values. So we have Rn equals this pile of junk less than or equal to this pile of junk. Basically what we're saying, it's the minimum of those two values. That's how that's how the code writes minimums. Okay, so that's what that means. And if you look at this expression, you'll see that some stuff is common. So for instance, if you look at the top and the bottom, both of these expressions carry this term over here on the right, UBS FUANT. It's the same on the top and the bottom. There's also a 0.6 on both of these terms here on the left. So what I can do is I can take this expression and I can simplify it quite a bit. Okay? So I think hopefully you find that this looks a lot more handleable than what was on the previous couple of slides. Now, the way that this works is you compute the tensile path capacity and the shear path capacity separately, and you just add them appropriately. Notice how both of the shear equation, or both of the shear components, have a 0.6. Where did the 0.6 come from? It came from the Mises yield criterion. Okay? Anytime that there is a shear failure, there is either a 0.6 explicitly built in the equation, or it's built into some of the values that you look up. Like for bolts, there's a lot of mechanics that go into the stress values that we look up, and we just use those directly. Everybody okay with this? Don't worry, we're gonna do a full-blown example on this. One other thing, one term that might be a little weird is this UBS. It's a block shear reduction coefficient, and 999 times out of 1,000, it's going to be 1 for us. The only time that it's not 1 is when we have what's called a coped beam. So you have a beam framing into another beam, and so you cut out, the top of this right here. The idea is so you can, have a beam right here. And so you cut out this little bit so that the floor is flat. It's called coping the beam. If you ever have a coped beam and you have multiple rows of bolts, you use UBS as 0.5, but other than that, every single time you take UBS to be 1. So we really aren't going to have to worry about that. Much like net area, it's possible that we have multiple failure paths that we need to analyze. So this one we have, 2 shear paths, 1 tension path. This one we have 1 shear path and a longer tension path. So which one governs? Well, it depends. Probably it's the one on the right, because there's less material you got to rip through. Okay? What we're going to do is we're going to take the example that we did, the problem that we did in example 4, and we're going to compute the block shear capacity of that problem on Friday. Okay? We're going to go through it very explicitly, step by step, and I think you'll find that this is pretty straightforward. Sound good? Don't forget, you got a present for me on Friday. That's all I got. I'll see you.